All around you, right this second, there's this invisible world in motion. It's governed by a secret set of rules. It's in the very air you're breathing and the water you drink. So today, we're going to decode those secrets. Let's dive right into the fascinating world of fluid mechanics. I mean, how is that even possible, right? You just give a gentle push with your foot, and this massive 2-ton car just grinds to a halt. It seems like it should be impossible. But this isn't magic, it's pure physics. And figuring out the answer to that question, well, that's our mission for the next few minutes. So the key to solving this whole mystery, it lies in this field of study right here. Fluid mechanics is basically the branch of physics that deals with everything fluids do, whether they're sitting still or zipping around. Honestly, it's the how behind, well, almost everything, from huge weather patterns down to the blood flowing in our veins. Okay, so a fluid is just a substance that flows when you push on it. Now, that sounds almost too simple, but it's absolutely crucial. See, when a physicist says fluid, they aren't just talking about water. Nope, they mean the air, the steam coming off your kettle, the oil in your car's engine, all of it. And this one simple idea, it's the foundation for literally everything we're about to get into. All right, so first up, let's look at what fluids do when they're just sitting there, not moving. This is called fluid statics, and believe it or not, this is where we're going to find our first big clue to stopping that 2-ton car. It all comes down to one thing: pressure. Think about it like this. If you've ever been deep in a swimming pool, you feel the pressure on you from all sides, right? Not just pushing down from the top. Well, that's the key concept here. Inside a contained fluid, say like the brake fluid in your car's brake lines, any pressure you apply is felt equally, everywhere, all at the same time, instantly. And there's actually a name for this rule, this scientific principle. It's called Pascal's law. And this one law, this is what makes the entire world of hydraulics possible. We're talking everything from giant construction cranes to the chair you sit in at the barbershop. So here's the big takeaway from Pascal's quote. If you push on a fluid inside a sealed container, you're not just pushing on that one little spot. Nope, you are instantly creating the exact same amount of pressure everywhere else in that container. It is a perfect system for sending force from one place to another. And this is where the real magic happens. Because pressure is just force divided by area, you can get really clever. Think about it. If you apply a small force to a small area, you create a certain amount of pressure. But if you take that same exact pressure and apply it to a much, much larger area, you get a huge force out on the other side. Okay, let's watch this play out with a classic example, the hydraulic lift. See that small piston on the left? It all starts with a little push there. That simple push pressurizes all the fluid inside. Now that pressure travels over and pushes up on the big piston on the right, the one with way more area. And the result? A massive upward force, enough to lift a whole car. Easy. A tiny bit of effort creates a giant result. And that brings us right back to where we started. Your foot on the brake pedal? That's the small force on the small piston. That creates pressure in the brake fluid, which then shoots through the lines to much larger pistons right at the wheels. And those big pistons, they clamp down on the brake pads with incredible force, stopping the car dead in its tracks. It's the exact same principle. Mystery solved. Okay, so that's what fluids do when they're sitting still. But what happens when they're actually moving? Well, now we're entering the world of fluid dynamics. And trust me, it's every bit as cool. So when it comes to flow, there are really two main ways it can happen. First, at low speeds, you get this beautiful, smooth, orderly state called laminar flow. Just picture honey slowly pouring from a jar, all the layers slide past each other perfectly. But then, when you speed things up, it all becomes chaotic and messy, with swirls and eddies everywhere. That's turbulent flow. Think more like a raging river. Now, a great way to understand moving fluids is to think of them as having an energy budget. They've only got so much energy, and they have to balance how they spent it. And the rule that governs this whole budget, it's one of the most famous names in all of physics, Bernoulli's principle. So according to Bernoulli, a fluid's total energy budget is made up of 3 accounts. You've got kinetic energy, which is from its speed, potential energy, which is from its height, and pressure energy. The total amount in the budget always stays the same. So if you take energy out of one account, you have to add it to another one to keep things balanced. And here it is, the single most important takeaway from all of this. Since the total energy has to stay constant, if you increase one type of energy, another type has to decrease. And the biggest, most important trade-off you need to know is this. Where the speed of a fluid increases, its pressure decreases. That's it. That's the secret.
So, where can we actually see this happen in the real world? A perfect example is a really clever device called a venturi meter. Its whole job is to measure how fast a fluid is flowing through a pipe.
Okay, check this out. As the fluid flows into that narrow section, the throat, it's forced to speed up, to squeeze through. It's just like when you put your thumb over the end of a garden hose, right? The water speeds up. Well, Bernoulli's principle tells us that since the speed just went way up, the pressure has to go way down. And by measuring exactly how much that pressure drops, engineers can figure out the exact flow rate. It's just a brilliant practical use of the principle. Okay, but here's the thing. Everything we've talked about so far, it kind of assumes we're in a perfect world with ideal fluids. But the real world, as you know, isn't so perfect. In reality, there's always a battle against resistance, a force we call drag. And when you're trying to beat drag, one thing matters more than anything else: shape. I mean, just look at the difference here. A streamlined body lets the fluid just glide smoothly right around it. But a blunt body, it just slams into the fluid, forces it apart, and creates this messy low-pressure wake behind it that literally sucks it backward. Shape is everything. And we can actually put some hard numbers on this. There's something called a drag coefficient, or CD, which is basically a score for how slippery an object is. So check out this data. A flat plate, just facing the flow head-on, has a really high drag score of 1.28. A sphere is way better, down at 0.47. But a truly streamlined body, get this, a tiny 0.04. That is more than 30 times less drag than the flat plate. Incredible. But hold on, it gets even more dramatic than that. Let's take that same flat plate. When it's facing the flow like a wall, it has to just smash the air out of the way. That creates a ton of drag. But what if you turn it 90 degrees, so it's parallel to the flow, like the edge of a knife? Now the air just glides right past. The only resistance is a little bit of friction on the surface. The difference is just staggering. We're talking over 600 times more drag when it's facing the wrong way. That just goes to show you how absolutely critical orientation is. Okay, so let's tie all of this together. We've looked at pressure, we've looked at flow, and we've looked at drag. And the thing to remember is these aren't just some abstract ideas from a physics textbook. No way. These are the fundamental tools that engineers use every single day to literally shape the world around us. So let's do a quick recap of our fluid mechanics toolkit. We've got Pascal's law, which lets us multiply force to do things like lift cars or stop trucks. Then there's Bernoulli's principle, where we trade pressure for speed to measure flow or, to help a plane fly. And finally, by understanding and mastering drag, we can design these incredibly efficient vehicles that just slice through the air. When you think about it, from the incredible power of a giant hydraulic press to the super delicate design of a race car's wing, we've really learned how to master these invisible forces. The principles themselves are fundamental, yeah? But their applications, they're completely limitless. Which really just leaves us with one final question to ponder. We've used these principles to lift, to stop, and to fly. What problems are we going to solve with them next?